Hey guys, so in the previous video, I talked about how the electric field should have a value of 0 on the boundaries of the wall. Because if the electric field has a value of 0 outside the wall, don't want the electric field to have any sudden jump from 0 to 2. If we want to go from 0 to 2, we need to go 0 0.01, 0 0.02, 0 0.03, all the way up to whatever value we want. So we want the electric field to be continuous and differentiable, or continuous and smoothly varying. Now, in the previous video also, I talked about the electric behavior of the electric field a lot, but everything I said also applies to the magnetic field. So now what we're going to talk about is how does a microwave actually heat food? So let's suppose we have an electric field. So here's an electric field pointing upward. If I place a dipole in the electric field, a dipole is a molecule with a positive and a negative side. So here's a dipole, here's the positive side of the molecule, here's the negative side of the molecule. If I place the molecule like this into that background electric field, the positive side of the molecule is going to be pulled in the direction of the electric field. The negative side of the molecule will be pulled opposite the direction of the electric field. And as a result, the molecule will tend to align with the direction of the electric field. Well, let's ask, what happens if the direction of the electric field changes? So if the direction of the electric field is now suddenly pointing downward, then this dipole molecule will see the direction of the electric field, and the dipole molecule will now flip its direction it's pointing. And if the direction of the electric field flips again, so now the electric field is pointing upwards again, the dipole molecule will now flip its direction when it sees the electric field change, and the dipole molecule will again flip to be pointing the way it was previously. One example of a dipole molecule that is very ubiquitous in food is water. Water has a positive side and a negative side. So water molecules will try to align with an electric field. Now, in a microwave, what's happening is we have an oscillating electric field. Now, I said microwaves have the wavelength of a couple centimeters, and a typical microwave in a house is going to be about 30, 40 centimeters across when it fits in your kitchen. So a microwave will only hold about 3 or 4 standing waves, give or take, depending on the size of the microwave oven you're using and just depending on the actual wavelength of the microwave light inside that oven. So here I drew a picture. I have 3 wavelengths of microwave light inside an oven. So here's one wavelength, here's a second wavelength, here's a third wavelength. Now, at some moment in time, the electric field inside this microwave is really strong here, and it's pointing upward. But at this location right here, the value of the electric field is 0. And at this location right here, the electric field is really strong and pointing downward. And at this location here, the value of the electric field is 0. And at this location right here, the value of the electric field is really large and pointing upward a lot. And at this here, the value of the electric field is really large but pointing downward. And we have this continuous very strong and positive, very strong and negative. And in between those locations, we have locations where the value of the electric field is just going to be 0. Now, this microwave must always have a value of 0 on the boundaries, but it is allowed to oscillate. So at one moment in time, the strength of the electric field is going to look something like this, where it's pointing up and large, then 0 pointing down, 0 pointing up and large, 0, on and on. At another time, a split second later, the microwave, the wave inside the cavity will look something like this, I'm drawing in green, where at this moment in time now, you still have a value of 0, you still have a value of 0 there, you still have a value of 0 here. But at this location, you have a really strong electric field that is pointing down. And at this location, you now have a really strong electric field pointing up. And at this location, you have a really strong electric field pointing down, and so on. So at some locations, the electric field is always going to be really strong, but keeps flipping between up and down. At other locations, the electric field is pretty much 0 at all times. And in between those locations, you have something in between those two. Now, the locations where the electric field is 0 at all times is called a node. So E equals 0 at all times is a node. And at the locations that are not nodes are called antinodes. So antinodes are the locations where the electric field is either pointing up at a maximum, or pointing downward at a maximum. So on this picture, the nodes would be right here, and here, and here. These are the nodes. And the antinodes would be the locations where the electric field is up in maximum or down in maximum at its greatest absolute value. So these would be the antinodes. So antinodes would be right here, right there, and right there. Now, let's think about what will water do if it's at a node or at an antinode. If water is located at a node, then the water, well, it doesn't really see any electric field, so the water won't do anything. But if a water molecule is located at an antinode, the water molecule is going to see a really strong electric field. And that water molecule, because the electric field is so strong, the water molecule is going to try to align with the direction of the electric field. And then the electric field will flip to the other direction, and the dipole molecule, the water, will flip its direction. And so at the location of the antinodes, the water molecules are going to really strongly flip, pointing one way then the other, one way then the other. At the locations of the nodes, water's not really going to do anything. Now, when the water is flipping up and down continuously back and forth, that's going to create a lot of friction, and that friction then becomes the thermal energy that heats your food. So food is only going to be heated at an antinode. Food will not be heated at a node. And that's why microwaves, the appliance, have a rotating plate, because if your food is rotating while all this is going on, the location of the node and the antinode is not going to change. But if the food moves around, then all your food will spend some time at the antinodes and get heated up. So what we're going to do is we are going to microwave a plate of some marshmallows. We will stop the microwave as soon as a few of the marshmallows begin to puff up. And the location where the marshmallows puff up will be the location of the antinodes. And if I measure the distance between the antinodes, so the distance from here to here, so this would be the distance between antinodes. Well, the distance between antinodes is just going to be 1/2 the wavelength of the light in the microwave, because the wavelength of light is going to run from peak to peak. So the wavelength is double the distance from the antinode. If I know the distance between the antinode and the frequency of light in the microwave, then I could use that to calculate the speed of light. Now, everything I described here, we were basically working in 1D. Microwaves are 3D objects. They have length, width, and depth, but they basically behave the same way. So this is going to be the end of the video. We're going to go microwave some marshmallows. We'll measure the distance between the marshmallows, and then we will be able to use that information to measure the speed of light. So what we're doing is we are going to microwave some marshmallows and then measure the distance between subsequent antinodes. There we have an antinode there and an antinode there. You could kind of see it beginning to puff up there and there. So let's measure the distance between these. So the distance between these antinodes is about 6.5 centimeters. So we also need the frequency of the microwave light in this microwave. So if we look on the microwave, we see that the frequency of the light is going to be 2,450 megahertz. So don't forget to do your SI conversion from megahertz to hertz when you're calculating frequency. And the microwave is about 32 centimeters across.